Hello, welcome to everyone in this video. This is our lecture number 2 of electronics, and this is the first part for the class for semiconductor diode and application. In the first lecture, we discuss about the network theory and on which we discuss about the Thevenin theorem, Norton theorem, superposition theorem, Kirchhoff Coulom's law, Kirchhoff voltage law, etc. maximum power transfer theorem, etc. We already discussed in lecture 1, and the problem asked in this lecture solved in the another series, that is the problem solution playlist. Okay, so in this YouTube channel you can get the different physics related video with theoretical part and some problem solution part in the different playlist. So if you want to, you can go to the description box, you will be get the different link for different playlist, you can watch them also, right? So in this video I want to discuss about the formation of PN junction, that is the diode formation, how the diode formation of semiconductor happening. We want to discuss these things, right? So let's start. You can see this is the syllabus for the BSc Physics Honors of Calcutta University. This portion, that is the part 1, we already discussed in the lecture 1. In the lecture 1 we discussed this one. In this lecture number 2, we want to discuss the PN junction semiconductor barrier, how this PN junction semiconductor barrier actually formed. In the upcoming session, we will be continue the later part of this syllabus. Okay, so you can see this is the total syllabus of this semester: PN junction, bipolar junction, field effect transistor, regulated power supply, and amplifier, feedback amplifier, op amp, operational amplifier, and so on. Okay, multivibrator, oscillator, etc. So that is the total syllabus for analog system and application. So we will be covered up in the upcoming session also. So in this video, I want to discuss about the formation of PN junction in semiconductor. Okay. So we want to start in the from the basic of the semiconductor, how the semiconductor are different from metal or insulator. We want to discuss from that point. Okay. So for that, we first wants to know about the energy band. What is energy band? We want to know about the energy band. Okay, what is energy band? Suppose you know from the Bohr's theory, that is, if there is one atom, a single atom, if you wants to draw the energy diagram of a single atom, this is a single atom. Okay, and this single atom, this is the nucleus. So for that, if you wants to draw the energy levels of electron, you can see this energy levels will be like that. This will be the energy level. Okay, and when the in the this is n equals to 1, this is n equals to 2, this is n equals to 3, this is n equals to 4, and so on. Okay, so these are the energy levels, okay. And the very high, this becomes energy band. So this is the energy levels. Okay, energy levels. But this is in case of a single atom, or if you consider the body, within that there is large number of atom, then what happen? If you consider there is large number of nucleus like that in a sequence, you will be get these energy levels like that. In the left hand, this is one, and these two are superimposed, that is this one and this one superimposed and resulting this like. Okay, so in every case in this between, this superimpose gives you like that. Okay, now the energy levels becomes like that. This is the energy levels of the atom. In the first portion, this becomes continuous like that. This is the, and this becomes like that, and so on. So now this level becomes band, because there is large numbers of level, there is large number of level arising here, there are also large number of levels presenting in this region. So this is called band, energy band. These are the energy band. So energy band is the collection of the energy levels. When the large number of energy level accumulated is called energy band. These energy band are mainly two types. These energy band are mainly two types. Number one, energy band are two type. Okay, energy band are two type. Number one, valence band. Valence band. So valence band is nothing. The band formed by these energy level of electron which are forming the valency. So band or collections of energy levels, of electrons which are used in valency. That is the when the electron are in valence, whose energy levels are combining forming the valence band. Suppose silicon, this form this valency, this electron is valency, the energy of this electron is valence electron. This is the valence electron. So energy level of this electron are combining forming the valence band. In the other side, another band is the conduction band. The conduction band. Okay, there is a conduction band. What is conduction band? Conduction band is the collection levels, energy levels of electron who are conducting. Okay, so this is the collections of energy levels, of electrons which are used for conduction. So this energy level used for the conduction is called the conduction band. So you can see the electron which are conducting, suppose you take any metal Au, there is some electron which are conducting, so the energy level of this electron is called conduction band. Okay, energy levels, that is the collection of the energy levels, is called band. So the two types electron, as one is the valence electron whose energy level is valence band, and another type is conduction electron whose energy levels is conduction band. Now my question is, whose energy level are higher, that is conduction band or valence band? Think, the valence electron which are connected within a bond, but in conduction electron which is free, so the energy of the conduction band must be greater than to energy of valence band. So you can say energy of conduction band must be greater than energy of valence band, because the electron which are conducting is more energetic than the valence electron, because in the valence electron they are bounded, they are stable compared to the conduction electron. That's why the energy level of the conduction band is higher than the energy level of valence band. So in band diagram, if you want to classify the metal semiconductor insulator in terms of band diagram, you can say band diagram, in terms of band diagram you can say that is the this is the conduction band, because conduction band is higher in compared to the valence band. This is the you can say this is the highest level of, this level is the highest highest level of valence band and valence electron valence band, and this is the lowest level means energy level of conduction band. So this separation, this is continue here and this is the continue here. Okay. This separation, that is the separation between the lowest level of conduction band and the highest level of valence band, is known as the band gap. This is known as the band gap. This is known as the band gap, EG. Okay. So in terms of band gap, we can discuss the metal, semiconductor, insulator. You know, in metal or conductor or metal, you can say in conductor or metal, you can say that is the conductivity is high. Conductivity is high, right? And in insulator conductivity is very poor, non-conducting. This is non-conducting. In between them, there is a material, that is the semiconductor, whose conductivity lies between these two material, conductor and insulator. And this semiconductor is important because its conductivity is tunable. Its conductivity tunable. That means we can change the conductivity according our requirement. That is the beauty of the semiconductor. In conductor, there is a conductivity is high, so that is not tunable, and the insulator conductivity is very low. This is also not tunable. But semiconductor, whose conductivity is moderate between conductor and insulator. That's why we can control or we can tune the conductivity of this material, and that is the beauty. We can use any device where we need to control the conductivity. Okay, that is the beauty. So in terms of band diagram, if you draw the band diagram of metal, semiconductor, insulator, this becomes like that. In metal, you know, there is a huge number of electron which are can conduct, and as well as the valency. So this is the band diagram of metal. In this region, there is a superposition between, this is the conduction band, this is the valence band, and this is the superposition of conduction band and valence band. Okay. So here you can say easily that is the Eg equals to 0. There is no band gap. Eg equals to 0. This is the conductor. This is the conductor or metal. So this is the band diagram of conductor or metal. In case of semiconductor, this gap will be certain value. This is the conduction band, this is the valence band, and this Eg is nearly 0.624 eV. Okay, 0.4 eV. This is the semiconductor, and this band gap can be tunable depending on the material or the alloy or the doping. Okay, so this is the band diagram of semiconductor, and the band diagram of insulator will be like that. This band gap is much larger, and this is above 7 eV, like that. Okay, so this is conduction band and this is the valence band. This is the insulator. Okay, so this is the band diagram of three main material: conductor, semiconductor, and insulator. So there is a band gap is 0. This band gap is nearly 0.624 eV, and this greater than 7 eV. And between 4 eV to 7 eV, there is a fluctuation, maybe semiconductor or insulator depending upon the material. Okay. Now comes into the point. So this is the band diagram of these three material. Now comes into the point. Uh, that is the temperature effect on metal and semiconductor. Now comes into the point, that is the temperature effect. Temperature effect on conductivity. Now that is the when we increase the temperature, then what will be the how the conductivity affected on conductor, semiconductor and insulator. When we increase the temperature of the material, then how the conductivity change. Okay. Now first comes into the point of conductor. Now if you comes into the conductor, in case of conductor, what happened? Suppose this is a conductor, and you know in conductor there is a large number of free electron. So there is a large number of free electron. There is a large number of free electron and nucleus also here, no problem. Now if you apply the voltage, the electron, if you apply the voltage, apply external voltage. That means if you apply this external voltage within that region. No, sorry. We want to discuss about the temperature effect. So apply external heat. Now if we apply the heat, okay, external heat, that is the increasing temperature. So increased temperature. What happened? The kinetic energy of the free electron will be increases. So kinetic energy of free electrons increases. So kinetic energy of free electron increases means velocity of electron increases. This higher velocity, because there is a congested area. Suppose this is a road and there is a large number of cars, and you have a bike and your bike speed above 100 km per hour. So you cannot control yourself to this like of path. Okay, then the collision will be increased. So when the velocity of electron is higher, then the collision will be increased. This higher collision is make the resistive. So higher resistive, because this flow of the electron is the current flow, and this making the collision, that means it becomes more resistive, that is conductivity is reduced. Higher resistive, that is reduced conductivity. So I think you clear about what happened in during the heat increase within the conductor. So this is the temperature and this is the conductivity. So if you increase the temperature, the conductivity will be reduced or fall down. So this nature will be like that, parabolic. Okay, this is the temperature effect on conductivity on conductor. Now if you compare in the semiconductor, if you compare in case of semiconductor in semiconductor there is no large number of free electron. There is a valence electron and some free electron. Suppose at 0 Kelvin temperature. At 0 Kelvin temperature, all electrons are in valence band. That means this is a conduction band and this is a valence band. All electron are like here. So all electron are like here. There are the valence band. The structure actually, this is the forehand structure or silicon will be in the all direction. Okay, so there is no electron outside this valence, that is at 0 Kelvin temperature. Now if you increase the temperature, what happen at T Kelvin temperature? At higher temperature, what happens? There's some electron are ejected from the valency. So at this temperature, suppose there is three electron are jump to the conduction band due to the temperature increases. So they are making a hole. What is hole? Suppose this is a silicon and this structure, all electron are in the valency. Now these electrons come out here. So there is a vacancy of electron. There is a vacancy of electron. This vacancy of electron known as the hole. Hole is not a particle. This is a vacancy of electron. This creates also current. That's why you consider the hole. So this is the vacancy of the electron. Okay. Now, if three electron comes out, the three electron comes out to conduction band. This is a conduction band and this is a valence band. So three electrons are comes out, then three hole making here. Okay. So here you can say number of hole. Here you can say number of hole in valence band equals to number of free electron in conduction band at T Kelvin temperature. At 0 Kelvin temperature, no free electron in conduction band, no hole in valence band. All electron are the valency electron in the valence band. Now, if you apply some temperature, then the higher energy escape this electron from valency to conduction band. So number of electron in conduction band must be equal to the number of hole in the valence band. Okay. So what happened here? Number one, if you increase the temperature, increasing temperature. So if you increasing the temperature, the energy thermal energy of electron increase, and this higher energy electron escape from this valence band. So higher energy electron escape from valence band. Higher energy electron escape from valence band. So making equal number of free electrons and holes. So this carrier, that is free electron and holes, free electrons and holes making current flow. So this making current flow, that means its conductivity will be increases. Conductivity will be increases. Conductivity will be increases. Conductivity will be increases. Okay. Now the plot will be like that. This is the temperature and this is the conductivity. So increasing temperature, the conductivity will be increases. So this is the plot for conductivity in semiconductor. This is in semiconductor. If you asked me how the hole can carry the current, electron carries the current, no problem, but how the electrons, how the hole making current. Suppose you have a electron series like that. Suppose these are the electrons. This is the free electron. This is the free electron, and this is the hole, and this is free electron. So these are the free electron. Free electron. Free electron means this is not bounded within this valency. Okay, and this is the hole. Now the next case, I think you understand what the hole and electron actually making here. You can see, suppose this is a silicon, and these are the electron in the valence band, and the one electron is ejected from those. So there is a hole, and this is the free electron. Okay, this is the free electron. So when this electron comes here, what image will be obtained? So hole becomes here, and the electron here, electron here, electron here, electron here, electron here, electron here. Next case, these become here. So hole here, electron here, electron here, electron here, electron here, again so on. So you can see the actually electron flow out, but you can see this hole become go to this that direction, and electron in the that direction. And you know the flow of electron is the opposite of current direction, so this is the direction of current. This is the direction of current. So hole can make the current flow, that is the conductor. So there is two carrier, one is electron, free electron, and another one is the hole. And in this case there is a large number of free electrons, there is no possibility to making the hole. So in the conductor there is only single free carrier, that is the free electron, and in semiconductor there is two types of carrier, free electron as well as the hole. Okay, so free electron in the conduction band and hole in the valence band, both making the conductivity. That's why the conductor becomes like that. And there is no such collision effect because there is few number of the electron presenting in the semiconductor. So there is because there is very few number of electron presenting within this semiconductor, that's why they are does not making the collision effect. Okay, what about the insulator? If you consider about the insulator, what about insulator when you increase the temperature? So insulator. So for insulator, the band diagram, this is very large, this band gap will be large, Eg is greater than 7 ev, like that. So if you want to comes this electron from that region, you need to keep up this large amount of energy, and this energy comes from heat energy. This energy comes from heat energy, and this higher heat energy comes from high temperature. This becomes high temperature. This required to high temperature, right? This required for higher heat energy, you need to require the high temperature, and this high temperature becomes the material burnout. Material, that is the material can be burn out. That's why the electron cannot go to that region. That's why in case of insulator, the material conductivity does not change with the temperature. So in conclusion, if you want to draw the temperature versus conductivity in three material, temperature versus conductivity of these three material, you can say in case of the semiconductor, in case of the conductor, this will be reduces like that. This is for conductor. In case of semiconductor, this will be like that. This is for semiconductor. This is for semiconductor. In case of insulator, this becomes like that, but this is very small at this region. So after that, this will be burned out. So this is for insulator. This is conductivity versus temperature. This is conductivity. This is conductivity. Sorry. This is conductivity versus temperature. This is conductivity versus temperature. Okay. If you wants to draw the resistivity versus temperature curve, this is resistivity, and this is temperature. This is temperature. Okay. So if you wants to draw the resistivity versus temperature curve, what happened? The conductivity reduce means resistivity increase. So in case of the conductor, the resistivity increase. So this is for conductor. In semiconductor, temperature increase, resistivity is reduces. So this becomes like that. This is for semiconductor, and resistivity is very high in case of the insulator. So this becomes like here. This is for insulator. Okay. So this is the diagram for conductivity and resistivity of conductor, semiconductor, and insulator. I think clear about all these things. Okay. So now comes into the point, that is how we can tune the conductivity of insulator, how we can tune the conductivity of semiconductor, because this is a tunable material. So how the conductivity can be tuned of semiconductor. Okay, there is two possibility. One already discussed, that is the temperature effect. So if you increase the temperature, the conductivity also increases, right? If you increase the temperature, conductivity also increases. But the temperature increasing is a cost effective method, and the material can be burned out up to a certain value. You can see that is the temperature increase, the conductivity will be increases, but at up to a certain value, the material can be burned out. At a certain value of T, material can be burned out. Okay, that's why this method is suitable for up to a certain temperature. After that, it cannot affect it. Okay, so you need to find out the another method. This another method is the doping. What is doping? Doping is the another type of material mixed with that one in a very few percentage, like 0.1 to 1%. Okay, 0.1 to 1%. Doping are making the material changeable conductivity. So you need to know about how this doping affect the conductivity of the semiconductor. There is two type of material can be doped here. So without doping, this is called intrinsic semiconductor, and with doping, this is called extrinsic semiconductor, because there is external type of material doped here or mixed out here. That's why this is called the extrinsic semiconductor, and this is the intrinsic semiconductor. So if you take, this is the first one is the p type. So if you want to making the p-type semiconductor, you need to dope the trivalent in the 4 valency material. So suppose this is a silicon matrix. Here you need to a trivalent material. Trivalent. So if you doped in the trivalent material, suppose aluminum. So in aluminum there is 3 electron present in this region, and these other things are silicon. Very few are present doped here, so other things will be unchanged. Only one silicon replace here. Okay, so you can see there is a hole generated. Okay, so in the energy diagram you can say at T Kelvin temperature, if there is 3 hole, they are making 3 electron in the conduction band, and this is in the valence band. Now due to doping effect, there are hole produced, uh, large number of hole produced. Okay, so these holes these hole produced due to doping, and these white color hole are produced due to temperature effect. Due to temperature effect, this hole and this electron also produced due to temperature effect. Okay, so you can say this number of holes are larger than this number of electron. In the previous case, this number of hole and number of electron are the equal. Number of hole and number of electron are equal. That's why you can say the Fermi energy level in between like that. So this is the EF, Fermi energy level. Fermi energy level. Okay, Fermi energy level. So this becomes like lies here. But in that case, you can say this is reduced here, so Fermi energy becomes like here, and this hole is accept the electron. That's why this is called acceptor level. Acceptor level. Okay, this is the acceptor level. This is the Fermi level actually becomes the acceptor level. Now here you can say number of hole is greater than number of electron. So number of hole in valence band, number of hole in valence band is greater than number of electron in conduction band. That's why the hole is positive. That's why hole is majority carrier. That's why hole is majority carrier. Majority carrier, because this is a large number compared to the electron, and this electrons become minority carrier. Okay, since the charge of the hole is positive, that's why this is called, since the charge of hole is positive, that's why it is called p-type semiconductor. Okay, that's why it is called p-type semiconductor. Now comes into the n-type semiconductor. What about n-type semiconductor? When you call n-type, you need to drop the pentavalent doping. You need to need the pentavalent doping. You need to know doping the pentavalent doping. Suppose pentavalent phosphorus. If you dope the phosphorus within that matrix, okay, within silicon matrix you dope the pentavalent. So 4 electron are linked to it silicon, no problem. But one excess electron in the pentavalent, one excess electron are making, this is the free electron. So in the band diagram, you can say there is making the three hole here, three electron here due to temperature, and this now these free electron making from this doping. So excess electron making here, this excess electron due to doping. So this band level, Fermi level is lies here, and there is large number of electrons. This is called donor level. Donor level. Okay, this is called donor level. This is conduction band. This is valence band. So here this electron. So number of electron in conduction band is greater than number of hole in valence band. Okay, number of electron in conduction band is greater than number of hole in valence band. Okay, number of electron in valence conduction. Since the number of electron is larger, that's why this is called n type. Okay, since number of electron is larger, that's why it is called n type. Okay, and number of electron is greater, that's why the electron here majority carrier. So majority carrier are the electron, and minority carrier is hole. Okay, now if I wants to discuss you the how the majority carrier, why the majority carrier arises, and why the minority carrier generate. If you wants to know, that is why majority carrier generated. The answer will be must doping. Doping is the cause for generate the majority carrier. And if I wants to know why minority carrier generated, the answer will be temperature. Temperature is the cause to generate the minority carrier. Temperature is the cause to generate the minority carrier. Now, if I wants to question you, that is the nature of electricity, nature of electricity or electric charge of n-type semiconductor. Option A positive, option B negative, option C neutral. Okay. The answer, what will be the answer? You must comment in the comment box. The nature of electric charge of n-type semiconductor. Option A positive, option B negative, option C neutral. Okay. So you must comment in the comment box answer of this question. Now comes into, so already formed the n-type and p-type semiconductor due to doping effect. Okay. Now if we combine this PN junction, what happens? So now comes into the main topic, that is the PN junction formation. PN junction, PN junction formation. How this PN junction form? Okay. So we know about the p-type semiconductor, n-type semiconductor. Now we want to making the junction here. Suppose this is a semiconductor bar. This is a semiconductor bar. Semiconductor bar. Okay. Of the semiconductor bar, in this region you doped the trivalent, that is aluminum, and this region doped the pentavalent. Example phosphorus. Okay. So when we drop the trivalent, you know they are produce large number of hole. Majority carrier are hole. Okay. Majority carrier are hole. And some electron here also, no problem. Minority carrier. In pentavalent, if you drop the pentavalent, there will be produce large number of majority carrier of electron. Majority carrier of electron produced, and some hole here also, that will be happening due to. So this will be p site, and this is n site, right? Now what happened at this junction? What happened? If you zoom out in this region, you can see that is trivalent means aluminum means like that, silicon, and this one electron is less, that is 3 are connected here, but here there is a hole, right? Hole. In the other side there is a phosphorus, right? Pentavalent. So in this pentavalent region, we can say four electron are valence, one excess electron produced, that is the free electron. So this free electron moves anywhere, but in this region, in this junction, this free electron can was this hole and this recombine. So what happened at junction? Electron hole recombination will be happen. So you can see at this junction, the electron from inside go to the p side, this captured or the trapped the hole, right? So next image will be like that. At the junction, what happened? These electrons comes here and this hole becomes it. So as a result, this charge of this aluminum will be negative because it accept the electron. So here this negative charge will be produced, and this eject the electron, this become positive. So in that region this become positive charge here. Okay, so this is n side, this is p side, and in the other hole here also, no problem, there is a hole, and this is the electron. Okay, so at this junction, these electrons from inside go to the p side. Electron from inside go to the p side, and this become positively charged and this become negatively charged. So you can say further this electron can go to that region, this electron can that region, and all these making negative and this making positive. But actually this not happen. Why this not happen? You can see, you can say here, that is you can say here, that is when this charge are making, you can say this is a parallel plate capacitor, like that. This is a plus charge and this is a minus charge, so this become parallel plate capacitor. Parallel plate capacitor, this become parallel plate capacitor. And you know this parallel plate capacitor making the electric field. So this is the electric field produced at the junction from this n side to p side, from n side to p side. From n side to p side produce the parallel plate, produce the electric field due to this parallel plate capacitor, n side to p side. Okay, so this become the electric field. Clear? This become the electric field. This electric field actually oppose the further recombination of electron hole. How? You know that is the force. Force is QE. F is the force, is the electric field, and Q is the charge. So you can say that is the force on electron in inside. So what will be the force on electron? That is charge of electron is minus E and this. So you can see the direction of the electric field and force or electron are opposite because this is a minus. The direction of electric field and the direction of the force on electron will be opposite. So this is the direction of electric field, that is the direction of electric field here. So force must be opposite. So when this electric field produced, then force on electron will be opposite to this electric field. So this is the force of electron, force on electron. In the similar way, hole, force on hole in p side. What will be the force on hole in p side? That is force on hole equals to EE, because the charge of this hole is plus E, charge of the electron is minus E, and charge of the hole is the plus E. So finally the force will be like that. The force will be like that on hole. So in the hole, the force direction will be same in the electric field direction. So field direction is like that. So force on the hole will be in that direction. Force on the hole will be that direction. Force on the hole will be that direction. So after making this fast recombination, this electric field produce, and this electric field produce opposed to further recombination. Okay, so this generated electric field, so generated electric field oppose to further recombination of electron hole. So this electric field opposed to further recombination of electron hole. Okay, that's why the this electron and hole are does not comes together. So in this junction, so at the junction there is no free carrier, because there is no hole, no free electron, so there is no free carrier. That's why this region is known as, that's why this region is known as depletion region. So this is the depletion region making, because there is no free carrier produced. And the electric field electric field electric field of depletion region opposed to further recombination of opposed to further recombination electric field of depletion region opposed to further recombination of electron hole. Okay, so finally this junction will be happen. Finally this junction will be happen here like that. This is p side, this is n side. In p side there are hole, and inside there are electron. These are the majority carrier, and this electron comes here, so this region is become negative and this is positive. This region is called the depletion region. Okay, so this is the PN junction formed. This is the called PN junction. This is called PN junction. Now if you wants to draw the energy band diagram of a PN junction, what will be at p side? At the p side, you know, the diagram will be like that. There is a acceptor level. This is p side, and the n side will be like that. This is the n side. Okay, this is the acceptor level, and this is the donor level. This is the acceptor level, and this is the donor level. If you combine these two things, finally you will be get this one. This acceptor level and donor level both are the Fermi level. Combinedly, this Fermi level draw at first. This is the Fermi level. This is the Fermi level. Okay. So with respect to Fermi level, this valence band here and conduction band here in the p side, and in the n side this is the uh, conduction band, and this is the valence band. So if you connect these two things, there will be the band diagram of this PN junction. This is the p side and this is the n side. This is the PN junction, and this region will be the depletion region. This is the depletion region. So this region is the depletion region, and this portion is the p side, and this portion is the n side. So you will be get the p side, n side portion of the region, and this is the depletion region. Okay. So in this process, the depletion region is formed, PN junction is formed. So if you know about this concentration, that is the charge concentration, acceptor or donor concentration, you can draw out here. In the next page I want to draw here. So here this region happen. So this is the plus charge. This is in this region, this electron making here, electron, and they are hole produced here, hole produced here. So this region is negatively charged, and this region produce positively charged. Okay, so if you know about the donor level, uh, donor concentration, if you know about the donor concentration, what happened? The donor concentration here largely happening in this region, and donor concentration largely happening there in this P site and that region. This is P site and this is N site. Okay, so donor concentration becomes like that. This is the donor concentration level. Donor concentration. In the opposite, if you know about the acceptor level, acceptor concentration, see acceptor concentration will be like that. There is a large number of acceptor and there is a less number of acceptor. This is the acceptor level. Acceptor level. This is the acceptor level. Okay. Okay. After that, if you want to know about the whole concentration, the whole concentration is largely here and there is no whole concentration here like that, and there is very few. So this is the curve of whole concentration. Whole concentration. And in the electron concentration will be like that. There is a large number of electron here and there is a zero number of electron. So this becomes like that. This is the electron. This is the electron concentration. Sorry. This is the electron concentration. Okay, this is the middle point. Yeah. So in this sorry depletion region, no whole concentration or electron concentration. Now comes into the space charge. What space charge will be happening here? Sorry, there is a positive space charge, there is a negative space charge. In the other two sides there is no. So within depletion region there is a positive space charge like that, and there is a sorry negative space charge like that. So finally, and in that two region there is no space charge. So this is negative space charge, this is positive space charge. So this is positive space charge and this is negative space charge. Space charge. Space charge. Okay. Now the field barrier, if you draw about the electric field, this is this electric field barrier. This electric field barrier will be like that. This negative, this, so this is the electric field barrier. Okay, and if you know about the potential barrier, this potential barrier will be like that. And that region, this is the potential barrier. Okay, this is the electrostatic potential. Electrostatic potential barrier. This is the electrostatic potential barrier. And finally, the potential energy for electron will be opposite. The electrons see this type of region. Okay, so this is the potential barrier for electron. This is the potential barrier for electron. Barrier for electron. Okay, So in the uh, final view of this energy band diagram of PN junction will be like that. This is the Fermi level, and this becomes like that. Okay, so this is p side, this is n side. There is a few in the p side, there is a few number of electron in the conduction band, and this is valence band, and there is a large number of hole in the valence band, right? In the opposite direction, there is a large number of electron in the conduction band and few number of hole in the valence band, conduction band, and this is the valence band, and this is the barrier potential VB. So VB is the barrier potential, barrier potential. So this amount of energy required to electron jump from this n side to the p side, jump from the n side to p side, this amount of energy is required, and this region is depletion region, this region is depletion region, and this is p side, this is n side. So how the PN junction is formed, I think you clear about the formation of the PN junction. Okay. And the PN junction circuit symbol, if you know about the circuit symbol, if you know about the circuit symbol, the circuit symbol will be like that, triangle, and this bar is n side and this triangle is p side. So this is the circuit symbol of a PN junction. So I think clear about this formation of the PN junction from the basic fundamental of this, and you must comment in the comment box within the answer of this question. That is the, where is this question? The nature of the electric charge of n-type semiconductor. Okay. So we just know about the formation of PN junction, energy level. In the next class, we will to continue from that point of view, the biasing of this PN junction and this definition, some conductivity, mobility, drift velocity definition, and after that we continue the biasing of a PN junction, that is forward bias, reverse bias, and their energy band diagram changes, then static and dynamic. After that, we know about the rectifier diagram, diode, that is the application of the diode, and the Zener diode, LED, photodiode, solar cell will be discussed in the next class. Okay, so I think clear. If there is any doubt, you must comment in the comment box. So that's it for today. This is all about me. This is my contact detail. You can connect me with this Telegram channel, and this is my online platform, and this is my YouTube channel details. Go to this channel, you will get different field related videos, some mathematical part also. Like this session, if you learn something from this session, share this video to your friends. Either he or she also get benefit from this video. Subscribe this channel if you new in this channel. Those already subscribed, thanks for subscription. Press the bell icon to get notification of upcoming video. So take care. We'll meet in the next video as soon as possible. Thank you.